Hello there. This video will focus on charged particles in magnetic fields and the motion that they'll go through. So we'll talk about the forces on wires and on charged particles in these fields, and then we'll move on to talk about how specifically for charges it will result in circular motion and how we can describe how that happens and the different relationships between the size of the charge, its mass, and how that relates to the shape of the path in terms of its radius when it's going in a circle. Here we go. So, what can experience a force in a magnetic field? We need moving charges. They might experience a force in a magnetic field. You can get a moving charge that won't experience a force in a magnetic field, and that's a very specific case that we'll talk about. But if we have moving charges, they can experience force in a magnetic field. It has to be moving. If the charge is stationary in the magnetic field, it will not feel a force due to that magnetic field. Now, because current in a wire or in a conductor is simply moving charges, if we have a current carrying conductor, they will also feel a force in a magnetic field and will get movement of the actual wire or conductor as well. We're going to start off this video by focusing on the current carrying conductors and how we determine the magnitude of the force and the direction of force for those, and then we'll move on to moving charges. So here is our wire carrying a current I through this magnetic field. This magnetic field here is going into the page, and we represent that with the crosses, magnetic field going into the page. This wire will feel a force because we've got moving charges in that magnetic field, and the magnitude of the force we can calculate using an equation. The equation we use to calculate how much force is this one here. The force is equal to the current times by the length of wire in the magnetic field multiplied by the strength of the magnetic field multiplied by the sine of the angle between the current and the magnetic field strength. So the current is just the current in the wire. For the length of wire in the magnetic field, we're talking about this length here that I've outlined in green, because that's the length of the wire that's actually in the field. So this is our lowercase l for how much the wire is in the field. And B, just our magnetic field strength. For our angle between this wire and the magnetic field in this example, it is 90 degrees because this current is going up and the magnetic field is going into the page. So the angle between those two vectors, up and into the page, they're perpendicular to each other. So the angle there will be 90 degrees. Now, if ever we get a case where the angle is 90 degrees, where our current and our magnetic field strength are at right angles to each other, the magnitude of the force is actually calculated a bit easy in that, because for an angle of 90 degrees, sine of 90 is just 1. So if the angle is not at 90 degrees, if we're calculating the force here in this example, we would end up just going I multiplied by L multiplied by B, and that would give us how big the force is. So the maximum amount of force is experienced if we are at an angle of 90 degrees between the current and the magnetic field strength. And we can just use ILB to work that out. If it is an angle, we have to multiply by the sine of the angle and work out what the angle is as well. So that's the equation we use to work out the force, the magnitude of the force. To calculate the direction, we use a special rule to do that. It's called the right-hand palm rule. And the way the right-hand palm rule works is you place your thumb in the direction of the current. So in this case, I'll place it up. We will place our fingers in the direction of the magnetic field. So these fingers here, they represent the little crosses for our magnetic field direction. And you'll be doing something like this, pointing your fingers into the page, and then your palm points in the direction of the force. And you should observe that if you do this with your hand, with your fingers going into the page and your thumb going up, the direction of the force is, for this one, it's going to be force to the left. So in this example here, it's force to the left, and we apply that same logic to calculate the direction of the force for any wire. So for this wire here, the entire thing will be shunted in a force to the left according to the right hand palm rule. So remember, thumb in the direction of the current, fingers, direction of the magnetic field, and then we slap, or our palm points in the direction of the force. So we'll look at some other examples here. So in this one here, we calculate the force in the same way. The current times by the length of the wire times by the magnetic field strength. And if you look at this example again, the angle between this magnetic field and the direction of the current is again 90 degrees. So we'd use just ILB to calculate how much force is on it, because we've got 90 degrees again. For the direction of the force on this one, we put our thumb downwards in the direction of the current. Then our fingers should be pointing like this for the direction of the magnetic field strength, and then you'll find that when you do that, your palm is actually pointing towards yourself, giving you that the direction of the force in this case should be out of the page and towards you. So the direction of the force in this case is out of the page. These next two examples here, we'll focus on this one. So again, to calculate the magnitude of the force, we use that same equation. F equals ILB sine theta. And in this question here, you should be able to see that theta actually has some meaning, because we actually have an angle between the current and the magnetic field strength. There's not 90 degrees this time, so we won't end up actually getting a force of just ILB. So we would end up having to use this angle here between the current and the direction of the magnetic field in red, and substitute that into the equation to calculate what the force is. For the direction of the force in this case, we want to point our thumb in the direction of the current, which is mostly going from left to right, and then our fingers in the direction of the magnetic field. And again, you should work out that it should be forced towards yourself and out of the page again. It's definitely going out to the page, because like in this case the only option is out of the page or into the page, and to be into the page we'd have to point our thumb to the left, and if you look at this example that shouldn't make any sense. So it's definitely going this way, and we definitely get a force that's going out of the page. For our last example here, the current and the magnetic field are well, not exactly in the same direction, but they're parallel to each other. If we've got a case where the current is parallel to the magnetic field, so this could be going up as well, and that would still be parallel to the magnetic field, then the amount of force the wire feels is 0. If the angle between the wire and the magnetic field is 0, there is no force experienced at all. You can also convince yourselves of this by looking at, well, the angle in this equation here will be 0. And if you substitute 0 in there, sine of 0 is 0, so the entire force just ends up being 0 as well. There is no force experienced here, and the wire just stays where it is. So there we have it, working with a wire and a magnetic field, calculating the magnitude of the force using this relationship here, and the direction using the right-hand palm rule. We'll move on now to talk about charges, and it's actually very similar, with a few added extra details that we just need to account for due to the sign of the charge, whether it's positive or negative. So it's not just current that experiences a force in a magnetic field. A moving charge will also experience a force in a magnetic field. So we've got these two charges here, positive and negative. They've both got a velocity. They're going to experience a force due to that magnetic field. Again, we can calculate the magnitude of the force using an equation, and it's very similar to the one that was used for current carrying conductors. Looks slightly different. So the equation looks like this. Force is equal to QVB sine theta instead of ILB sine theta, where we multiply the charge by the velocity, by the magnetic field strength, by the sine of the angle. This time the angle is between the velocity and the magnetic field strength rather than the current and the magnetic field strength. It's very, very similar, and it's used in a similar way because if we look at this example, this positive charge has a velocity, and the angle between this velocity and this magnetic field going into the page is again 90 degrees. And if we substitute 90 degrees into this equation, we get sine of 90, which is 1, and the equation again just becomes F equals QVB. So if we have a case where the velocity is at right angles to the magnetic field, we get a force that's equal to QVB, and we don't need to worry about the sine theta bit. So in this example here, if I were to calculate the force there will be equal to QVB. Hang on. QVB like that. So that's how we calculate the magnitude of the force and how we can relate it to charge, velocity, and magnetic field strength. To determine direction, again we use the right-hand palm rule, and the only difference is that this time our thumb points in the direction of the velocity rather than the direction of the current. But when you think about it, the direction your thumb pointer is kind of the direction of the charge in the current, so nothing's really changed. But we do need to make a distinction whether we're talking about positive charges or negative charges. So we'll look at the positive charge first, because that's typically the same way we do it for a wire. So if we put our thumb in the direction of the current, fingers in the direction of the magnetic field, we should find for this example that the force on this positive charge is going to be to the left at this point in time. There we go, it's forced to the left. For the negative charge, we need to remember that it is forced in the opposite direction that we do when we use the right hand rule. Because if you put the thumb in the direction of the velocity here, fingers in the direction of the magnetic field strength, we will end up with the same thing. The palm of our hand will point to the left and seems to suggest that it's being forced to the left. But for a negative charge, it's forced in the opposite direction because it's a negative charge. So I tend to think of it as if it's negative, you point your palm in the opposite direction and you end up kind of backslapping the electron or the negative ion in the opposite direction. So the negative charge is going to be forced in the opposite direction to positive charges. So for this one here, the force on it will be in this direction, going from left to right, like that. So that will be the direction of the force for a negative charge in this example here. So using this logic and applying the right-hand rule, where the thumb is in the direction of the velocity, the fingers are in the direction of the magnetic field, and the palm is in the direction of the force. But we just remember a little proviso that we need to reverse the direction of the force for a negative charge. Or you can think of it as kind of backslapping for the negative charge like I do. So this example here, we'll look at the force for the positive charge. Thumb will be going down, fingers should be going from left to right, and you should find that your palm is pointing towards yourself. For a positive charge, that's the direction of the force. So for this positive charge, it's forced out of the page. For the negative charge, when we end up using our palm, we end up making the same shape with our hand, but we need to remember it's a negative charge, it's forced in the opposite direction, so this negative charge will be forced into the page instead. There we go. And again, for this example, for the magnitude of the force, these velocities are at right angles to the magnetic field strength, so the amount of force will be given by QVB, because sine theta will end up being 1 for the 90 degrees. So we end up multiplying whatever these charges are times by the magnitude of their velocities times by the magnetic field strength, and we can relate them to the force in that way. Two more examples to finish off. In this example here, our velocity is clearly at an angle to this magnetic field. So if we were calculating the magnitude, the force would be QVB sine theta. Where theta is the angle between this magnetic field line and the velocity. To do the direction, we point our thumb in the direction of the velocity and our fingers in the direction of the magnetic field, and you should find that it's being forced out of the page. That's assuming that it's a positive charge. So if it was a negative charge, it would be in the opposite direction into the page instead. And to finish off this last one, where we've got velocities, either if it's positive or negative, that are parallel to the magnetic field. And just like with current carrying wires, if we've ever got a case where the velocity of the charged particle is parallel to the magnetic field, we get zero force, no force at all, just like it is for current carrying wires. So we no need to calculate direction because there is no force. F equals 0 in this particular case. I'll finish this off here. Stay tuned for part 2 of this video.